So we've gone through this detail of now the pseudocapacitor materials. And so now I can tell you, we can talk, so we've gone through the intrinsic materials, and I've given you an example there. And now what I want to do in the remaining extrinsic materials, and these are now going to be battery-type materials that normally show things that we want. They're usually slow materials, but we're going to do something to them, and we're going to make them to pseudocapacitors so they have high energy density and high power density. And so the place to start with this, as I call it, this extrinsic pseudocapacitance, is molybdenum dioxide. Now, molybdenum dioxide is one of those rare ceramic materials which is metallically conducting. Its structure, you can see that there are tunnels there, and it's been investigated very well by the battery community to make sure that lithium can go into the structure and out of the structure without a problem. And it does go in and out of the structure, but the problem is that you get a phase change. And so you will start with the monoclinic phase, but then you will, the material will then transform to the orthorhombic phase, and this of course takes time. And so for this reason, the material has really not been looked at in any detail. When we make this as a nanoscale material, it's a nanomaterial, and not even that nano, 15 to 20 nanometers, which you can readily do by hydrothermal synthesis, then what happens is that you can now suppress the phase transition. So here's our micron-sized powders. You can see that you have splitting of the various peaks, that indicating that you're going through the phase transition, whereas if you go to nano size, there is no phase transition. No phase transition, that's a good sign, because it means we can now start to think about how do we make this into a pseudocapacitor material. And to make a long story sort of shortened, one very good way you can do this is first, in your synthetic approach, is to put in graphene oxide. And under hydrothermal conditions, it'll reduce graphene oxide. So basically, you're able to put the molybdenum dioxide nanoparticles that you see here on very thin sheets of graphene. We like the thin sheets of graphene because they serve as current collectors. And they give good charge transfer properties, which again is something that we need to have. So there's various studies on why this works and why it anchors very well, but the bottom line is that it does work extremely well. And when we make these materials, we find that we don't have to worry about phase transition. We retain the alpha phase of we retain the monoclinic phase of the molybdenum dioxide. We also find from the Raman spectroscopy that we are having an appropriate D and G peaks that appear. And also in the XPS, we learned that we have removed most of the oxygen from the system. We have really made a very good material here. And now when we go to the electrochemistry, we find some very nice results. When we go to the galvanostatic experiments, which is constant current again, we see that 50 C corresponds to almost a minute, 1 minute charge and discharge. We can get energy densities on the order of 150 milliamp hours per gram. As I indicated before, that's what battery materials are today. So it's a very impressive feature. It's just that you're operating at roughly 20 times higher than what battery materials can do. This is another experiment related to the sweep rate. And again, the difference here between the material that's on the RGO and the reduced graphene oxide versus the material that doesn't have that, you can see is a factor of 2. And again, a very important result for us. Okay, and then move forward just to summarize this part of the talk then. So what we've seen with molybdenum dioxide is we can make it into an extrinsic pseudocapacitor. And the reason we're able to do that is because we're able to make it as a nanoscale material, and we suppress the phase transition. And so from that, the real victory here is the ability to get this type of a value of 150 milliamp hours per gram and to get it at 50 C. As I indicated, 60 C represents a 1 minute charge and discharge. So this is just a little bit slower than a minute. Just to show you how this compares with other materials, again, here's our energy density on this scale. This is the C rate, so this is the discharge rate. It's how much power you're getting out of it. Almost all the cathode materials, and for that matter, the anode materials that are used in batteries, they operate maybe at most at 10 C, so a 6 minute charge and discharge. You can see that niobium oxide is out there alone at these very, very short, very high rate conditions. And when we go and compare that now to other systems, lithium titanium oxide is a nice one to compare it to because there's commercial products with that. Niobium oxide is better than the lithium titanium oxide, and even better than that is what we saw before with the molybdenum dioxide on the reduced graphene oxide. So again, it shows that you're able to do this very nicely, and you are able to with materials that operate at very high charge rates and still retain their high energy density. There are other approaches we can use to this for pseudocapacitance. One way is to work with what's called two-dimensional materials. There's a lot of interest in taking materials and exfoliating them by various means. We've done this, and others have as well, with titanium dioxide. And so now we have sheets of material, we have large amount of surface area, and we notice also that our redox peaks are changed, and that has to do with this very subtle structural change that happens in a two-dimensional structure. But from the electrochemical standpoint, we find that B is equal to 1. We also find that the voltage offset is very, very low until you get to very high C rates. And what we find, once again, with this material is that we're able to retain a very nice bit of energy density in the titanium oxide nanosheets that are, in this case, an electrochemical experiment, at a very high sweep rate. So again, what we're seeing is, same message, high energy density at high rate. But this time, it's not by making nanoparticles, it's by going through a two-dimensional route. There are other routes. Another route we like very much is to make mesoporous materials. In this case, what you synthesize a material using solid gel chemistry, but you also have a structure-directing agent. You burn out the structure-directing agent, and you're left with a mesoporous material. It's a wonderful architecture because the electrolyte, the liquid electrolyte, is able to penetrate through the pores. The walls you can control very well. They can be very thin. We know that as we make dimensions on the order of 10 nanometers, materials all begin to look like pseudocapacitors. So this part works extremely well. The porosity for the electrolyte is interconnected, so there's very good access of the lithium ions to the walls of the material. And then a final approach is to make oxygen-deficient materials, and this is to improve the electronic conductivity of these materials. And this is work that is just starting and that is just beginning to percolate through the community. And the idea is that maybe you have to get away from stoichiometric materials, go to non-stoichiometric materials. You'll improve the electronic conductivity, and you can now also induce pseudocapacitance in the proper morphology. So I've more or less come to the end of this. Of the talk, so let me review what I've tried to get across. First of all, the idea that we're going to be designing ceramics in the next generation energy storage systems, those are the ones up over here. Again, the key word is you want to have the energy density of a lithium-ion battery, the power density of a supercapacitor. And so we're just beginning to start to understand what those materials are. We've begun to see what these different types of characteristics are, and you've seen about this B equal 1, because we're now all we're card-carrying electrochemists, but we also are reaching these types of very impressive energy densities of 100 milliamp hours per gram at 100 C, and you have to realize that's less than 30 seconds, or on the order of 30-second charge and discharge. So again, we've seen some of the metrics that we can use to characterize these materials. To some degree, we are discovering materials. To some degree, we are rediscovering materials. So now and it has to do with the fact that we understand this issue about phase transitions and also the ability to suppress phase transitions. And then something which I think bodes very well in this area for these next generation materials has to do with the fact that we've already identified numerous extrinsic routes for creating pseudocapacitance. So with that, let me just review what I hope to get across in this lecture. I've made a good case for energy storage, and I hope I have. These are things we often see in the newspapers and magazines, and so I think that we really can say that that energy storage is something that we're going to need to improve in the years ahead. There's just too many applications and reasons why we have to do this. We've identified that ceramic materials certainly are very much front and center involved in these materials. I talked about the core shell materials, the pore solid architectures, and also phase transitions and the like. Again, these are common themes in material science. We have a lot to learn from different parts of material. And finally, in terms of where are we today, in my estimation, the enabling science and technology is what's being developed in our laboratories, and also in laboratories, not only at universities, but national laboratories, and also in industry. So with that, let me thank the audience, let me thank the organizers for the opportunity to come, and I'll be happy to answer questions, of course. Bye.